Everyone, and welcome to this yet another session on this is our sixth mission or the sixth masterclass on Kubernetes. So welcome to this masterclass. This is part of our Kubernetes bootcamp or Kubernetes dojo. And let me just review what we did last week, and we will get started with this week's agenda as well. Just give me one quick moment to share my screen one more time. How is everyone doing? You can put it in the chat. We're doing a live stream on YouTube. We're also streaming this or conducting this live on Zoom. So the members who are part of our School After Hours community are joining through the Zoom sessions, and everyone else can join through the YouTube live as well. So if you have questions, post it during the session. You can post it, I will check in with you at a regular interval anyways. So if you have any questions, start posting those, and feel free to say hello. Would love to know where you are joining from. So if you, just type in where you're joining from in the chat. We would love to know where all of us, all of the members and non-members are kind of joining from. Just give me one quick moment. All right. Yeah, I had to switch off my phone. All right, so we have Bibek joining from Nepal. We have Malay Sikani, who's joining from Malaysia. Great to know that. Just to let you know this, once we are done with this boot camp, I'm planning a short vacation during my kids' holidays, and that's going to be Malaysia. So I'll be in Malaysia during the first week of April, about 10 days. So great to know we have people in our community and joining this session from Malaysia as well. All right, so we have Harish, we have on the Zoom, we have Cedric, we have Dinesh, we have Janmajay, Pradeep, Teja. Welcome everyone, and let's begin. So this is where we stand right now. We're talking about the Kubernetes Bootcamp. And we started with the first mission where we learned about containerizing the application, learned how to deploy things with pods, learned to scale applications using replica sets, auto scaling as well. We also learned about networking concepts. We dive deeper into networking, ingress, all these topics. We took a break for a week, and then we came back last week, talked about deployments. We're gonna talk about persistent storage today. Something which is very interesting if you want to run persistent applications like databases, or something which needs to store some state, even clustered databases and whatnot. And for that, what are the primitives that Kubernetes offers you? We will talk about that. We will touch base on some additional controllers like statefulsets and DaemonSets as well. And then next week, we will talk about security, HEM, production, like structure, infrastructure, building that, administration, and finally, we'll go on talk about Argo CD as well. So we are at mission number 6 here. That's because this was just a project. Before that, actually, it was a project. So this became mission number 5. And we are on mission number 6 per se, where we are talking about persistent databases. All right. So Cedric has a question about recordings. Recordings are available on YouTube channel automatically because we're streaming there. We post it on the site as well. I will tell you where to find it. So if you log into schoolofdevops.com, and once you're logged in and go to the dashboard, you have basically from the dashboard, let me log in and show you. You have to go to the boot camps or the dojo, and there you will find the recordings and the course created for that. So if I go to the dashboard, this is where you have access to everything from, right? This is like your dashboard to go to dashboard 2. And from here, if you go to the dojos, and you can search directly or jump directly using a URL as well. And this Kubernetes Bootcamp is where you'll find all the content, including the courses, as well as, let's say, the projects, as well as the archives. So this is the archive. So this is where you'll find everything until the session number 4. I'll add the 5 and 6 now. So it's there. 5 is there. It's just on the sequencing is not right. So this is where you'll find all the recordings at, right? So this is just one place where you'll find everything from. All right. So if it does not appear, we will look into that as well. If you can share your screen a little later, we will look into it towards the end of the session. All right. Now, let's get started with today's topic. We're going to talk about the storage and persistent storage at that. And why would you want to talk about this is sometimes we want to run applications which have states. Sometimes we want to run databases as well with Kubernetes. A lot of times what we do end up doing is, since database is very critical, we end up running it outside of Kubernetes, maybe using a managed service, and then connect to that from the Kubernetes infrastructure, which is fine as well. But if you decide to run database with Kubernetes or any other stateful application, including, technologies like Cassandra and so on, right? MongoDB and, or any, even Postgres and databases like that, you could still use Statefulset to do so as well. What makes Statefulset special? Will talk about that once we understand the storage concepts first, because each of this application is going to require some sort of a persistent storage, right? So persistent storage is where we talk about the volumes first. We'll touch base on all sort of volume related concepts and so on, and then we will take up the concepts related to stateful set. So don't worry about what's in this on the screen right now. I'm just taking it to you know the slide where I will begin explaining stateful sets well. Before we touch base on stateful set and running the stateful application in a certain way, we need to understand how to provide the volumes to the applications, right? And we've seen a little bit of that earlier. If you remember, let me take you to the screen here. And if you remember, we deployed the pods. So the second mission was where we talked about pods. And one of the pods that we deployed was DB to run this application called as Postgres as a container. And you can see that it's an image called as Postgres 9.4. And here we used a volume. So there are two things that we added and talked about when we touched base on this. One was the volume, second was a volume mount. Now, what is the difference? The difference is volume is given to the pod, right? And pod is a collection of one or more containers. Let me explain that. Pod can contain one or more containers, right? So this is your container and this is your pod. You may have a sidecar or whatnot. And this is the reason why I say that volume, when it is created, it can be an external volume, but the volume is associated with the pod basically in some way, right? And volume is given to the pod, and then you can take this volume and mount it inside the container. You can take this volume and mount it inside the container so that your application can consume it at some point in time, right? So that's how we define it. So volume is a part of the pod spec. This is the pod spec, and volume is part of that pod spec here. And then you take this volume called as DB data, whatever type of volume it could be, and then you mount it inside the container, right? So you have a volume mount here. So you take this volume, whatever you defined here, and mount it inside the container. Now, if you keep on attaching the volume directly to the pod, it is a problem because pods can come and go. Every time that you have a new version of the application, you're going to relaunch the pod, meaning delete the previous pod, and that will be replaced with another. Now, what happens when that is deleted and so on, is where instead of creating a volume this way, you use something else called as a persistent volume claim, a volume claim rather. And instead of defining the volume right here, you keep it that configuration separate in a separate configuration called as a persistent volume claim, right? And to that, you have a volume associated with it. So how does this work? And what was the problem with the initial versions of, let's say, Kubernetes? And how was that solved later to dynamically provision the volume and so on is what we're going to talk about now. I'll start explaining this concept by playing bits of this video. I'll probably put a link to this video at the end of it as well, or in the live session, the video recording here. So let's talk about the volume in Kubernetes. Let me share it again with the audio. All right, here we go.
And let's go over the Kubernetes storage model. So with Kubernetes, an administrator has to create persistent volumes in a pool. So a persistent volume is a base abstraction for a piece of storage. So it has a size, and it's backed by something like NFS or iSCSI or Google Cloud or whatever. A developer now who needs some storage will submit a persistent volume claim, which is a request for a certain amount of storage. And then they will reference that claim in their pod. And now Kubernetes can match up the exact volume with whatever the pod needs. So this is so far so good. The problem with this is that this requires the admin to provision these volumes in advance, which is not how we think of other resources like CPU or memory. So what if you want to just create those volumes on demand?
All right. Before we start talking about the next concept, let's understand this, right? So the concept of volumes and volume claims, etc. So let's say when you need a volume, you're a user. That's why I've divided this into two sections. You are a user and you need a volume for your application. How do you go about it is where you have the pod spec, where you have a container. Container defines the volume mount, and then volume mount is referencing a volume. So we define a volume, and then that is what gets mounted here. Now, this volume, the actual definition of that volume, what kind of volume and all that, is then delegated to the persistent volume claim. Why? So that when the volume is given, it is associated with the claim, right? And even if the pod gets recreated, you have a new version of it, you delete the pod, recreate the pod, you have multiple pods, whatever it is, you can still reference the claim. As long as the claim exists, the volume will remain, and you can connect to that and start consuming it and so on. Now, how does this claim thing work? So what you define in the claim is mainly 3 to 4 things. The 4 things that you define include the type of the storage that you need, like you need a cloud storage, for example, or NFS storage or iSCSI, whatever is available in the cluster. I lost connection to my iPad. Let me just connect it back again. It's taking a little longer. Just give me a minute. Yep. All right. There seems to be some issue. Never mind. We'll continue with the discussion. So basically, when you need a volume and how it gets provisioned is you ask for a storage using the persistent volume claim. The claim is like an insurance claim, right? So let's say you bought a car insurance policy and you hit your car. Now you have to claim. You raise a claim with all the details of what happened and all of that description of it. And then that is looked at by an administrator. An administrator would basically approve some amount and give it to an associated with the claim and so on. So it's a similar thing. It's just that you're asking for a volume or claiming what you're claiming for a volume, and you define all the properties of that, like what kind of storage that you need. Let's say you have a NFS or there's a AWS EBS volume or whatever it is, right? So you define what kind of storage you want. You define how much. You define how it should be mounted, the permissions of that, and you define whether it is a file system, like you mount it and use it, or you want to use it as a device and format it yourself and so on. So there are 3 to 4 things that you define in a claim, and then administrator has to look at the claim and create the volume for you. And that is how it worked until about 1.16 version of Kubernetes, when they changed it. Because for this, you understand the problem, right? So somebody has to be there, an administrator has to come in and look at the claim, create the volume for you, and only then will you get it. If you're doing that in the middle of the night, you have to wait for someone to wake up and come back and do that, right? That's not how things work in Kubernetes otherwise. When you ask for a pod, you ask for more replicas, it creates automatically, the scheduling happens automatically. So how do you automate this process of creating the volume is where there was a concept called a storage class was introduced. Let's hear it out from this video first.
So the alternative is called dynamic provisioning, and that's done with storage classes. So instead of the admin creating those volumes directly, the administrator will create a couple of different profiles of storage that they want to provide. So let's say fast storage is always provisioned on SSD, slow storage is provisioned on hard drives. Now a developer does exactly the same thing. They claim, or they submit a persistent volume claim, but that volume is only created at the moment that that claim is submitted and then attached to the pod. So for Kubernetes, this is the base model of how you do storage.
All right. So what happens with the storage class is like an automation here. Storage class is like a bot sitting there in the cluster looking for the volume claims. And as soon as you create the claim, storage class will automatically go ahead and start the provisioning of the volume. Now, how does that happen is where there is a concept of provisioners actually. So let me take you to the documentation related to storage classes. And explain the provisioner concept as well. See storage class here. So instead of administrator going ahead and creating the volume when you need it or when you ask for and so on, they just define how that volume should be provisioned in an automated way. And for that, there is a storage class configuration. Now, how does that provisioning actually work is where you have either an automated provisioning, like uh, if you look at this storage set of storage classes here, right? So there are different classes of storage available here, for example, that Kubernetes supports. And some have internal provisioner checked in front of them, some don't. So what is the difference? Let's say if you ask for a geo-file, or if you ask for Portworx volume or vSphere volume, Kubernetes all internally has the capability of connecting to that storage system and automatically provisioning the volume for you. So that code is built into the Kubernetes, and that's why it has this internal provisioner along with it, right? Whereas some, like NFS, for example, or a local storage class, it does not have an internal provisioner, meaning here you have to run something. So you define a storage class, and in addition to that, you run something inside the cluster, a pod basically, which is doing that provisioning. And that is where you have the external provisioner. So either you have an internal provisioner where Kubernetes comes with the code, or if that is not the case, you run a pod which will act like a storage system, or which will interface with the backend storage system that you have, let's say NFS or maybe CephFS or whatever it is. And then it would go ahead and connect to that and create the volume and make it available to your pod through the persistent volume claim. That is how the dynamic storage provisioning actually works, basically, right? Now, this is also changing a little bit, but I'll show you how this works until this part, where I will be demonstrating to you how I would create a volume for a database like this. And this time, I'm going to create a deployment for the database. We are talking about the same use case that we have been following, this one. And we will, let's say we have deployed the vote application, connected it with the Redis application. This time we want to run a database, which is the Postgres application. And this needs a persistent storage for sure. And this is where I would create a deployment which would connect to a persistent volume claim. And that claim will automatically define, or claim will define what kind of volume I need. And that will be provisioned via the storage class, which is already available in the cluster. So I'll show you that cycle, and I'll let you explore that code or take you through the code as well. So I'm going to run DB deployment, this time with a persistent volume claim. So if you look at this is a deployment by name DB, whose spec is here, which has a volume. In this case, there is a volume and volume mount both. The volume is a pod spec, and you have a volume called as DB vol. But pod does not create a volume, or it is not directly created here, but it references the persistent volume claim called as db-pvc. So everything related to how the volume should be created, what type, and all of that will be part of the DB persistent volume claim configuration, right? Here it will just create a volume and mount it to this container. Let's find out how this works when I deploy it. I will also I'll start watching a few things here. The few things that I would watch include pods. I will watch for the persistent volume and persistent volume claim and the storage class. Okay. You see, I'm looking for the pods, the Redis and both pods right now. There seems to be a storage class created. Who created this? I've used a tool called as kind to set up this cluster. So when I set up this cluster, the storage class was automatically created, the configuration for that. That is why you see this. Okay. There is no pod for the database yet. Okay. I'm yet to create it. There is no volume. There is no volume claim. This storage class is a local storage class here of type local, basically here. So that's why it does not have the internal provisioner. So it has to rely on some provisioner, which is also part of this cluster. I'll show you where. So where is the provisioner? It is running in its own namespace. This is the provisioner called as local path provisioner, and it is running in this namespace, and it is watching for the claims of this type local paths as a storage driver. And if it finds any persistent volume claim with that, it is going to create uh, a volume on its own. Okay, that's what it will do. Okay, so this is what is happening here. I will also show you what's happening with my uh, provisioner here. So if I show the provisioner logs, I'll open another window and show you there. Yeah, you see local path provisioner working here. What it will do is constantly watches for a persistent volume claim. It's a provisioner. Its job is to provision the volumes of type storage class here, where whatever the storage class is defined of that type, basically. The name of the storage class, which is defined in the cluster, is called as standard. So if I ask for a volume of type standard, this provisioner will come into play, and then it will automatically create a volume associated with the pod and so on. So what I'm going to do is first begin by launching the pod deployment, which will create the pod, right? I'm going to launch a deployment for the database here, and that will try to create a or reference a volume claim and create a volume of whatever type it has been defined in the claim, and then mount it here. That's what this will try to do. And when I apply and see what happens, you're going to notice that it starts launching a pod, which is in a pending state right now. Nothing happens. If you come back after, let's say, 10 minutes, you're going to see the same state. Why is the case? We'll find out. If it is pending, the problem is typically in the scheduling part. So I'm going to look at the, not the logs first. I like use describe. And here it tells me why the problem, what the problem is. It's a scheduling problem, as we talked about. And if it is pending, it's mainly because scheduler is not able to launch it or find a node for it. The reason for that is it's dependent on something which does not exist. That is the persistent volume claim. Now I have the code for it. The volume claim does not exist. Sure, but I have the code available for it. So what volume claim it is looking for? It is dbpvc. That's part of my configuration here. I have the code to create that volume claim. And here I have defined 4 properties, right? What are the 4 properties? What type of storage I need? In this case, I say NFS. I'll have to change that. How much? 2 gigs. What are the permissions or for a node to attach this volume with? It says read write one. So it will be only attached to one node. It's not particular pod, but node. Remember that. And it will just be mounted as a normal file system. So if I want to create a volume that is available in this cluster, there's only one type of storage available called as standard. That is the name of the storage class. So I have to ask for a standard volume, or if I omit that, and if there is a default storage class setup, it will automatically pick that up anyways. In this case, I will change this property to whatever storage class or type of storage available in the cluster called as standard. And as soon as I do that, see what happens here. It's provisioner watching for this persistent volume claim of type standard. Okay, nothing happened here. It just created a claim which is in a pending state. Yeah, because the provisioner has not yet found that claim, and it will look up, it will create the volume, and it will basically start uh, creating the volume, and it will associate it with this claim. That's what should happen. Generally, it happens by now. Should have happened by now. The volume should have been created. Just going to check the name. Yeah, everything seems fine. Just wait for a moment, or else I'll have to reset something here. Generally, the storage provisioners have access cluster wide, and it will automatically start launching, creating the volume and so on. Should have happened by now. All right. Let's find out what's going on here, as well as what does it show us right now. If you describe. It's not able to find the claim. We seem to have one. I'm also going to check the namespace I'm in. The correct namespace. This is fine. The storage class exists. Provisioner exists. Consumer, we already have consumer, as in the pod is looking for this claim. All of that looks fine. Now, how do we debug now? One thing I'm going to do is, this has been running for a while. I'm just going to reset this or recreate this provisioner by just deleting this one. We'll find out what happens. Before I hit this, I will check one more time. So this has been run via some deployment or equivalent, maybe a stateful set or a deployment. So it will automatically come back. A new one will be launched. It's not a stateful, it's a deployment. So it will be relaunched, this pod. And when that happens, we'll find out if it goes and provisions it or not. You see, it's started the provisioner with a new name. It has created the volume. So I think there was a problem with the provisioner. And this is one way to fix it, actually, depending on what the problem could be and so on. right? You see, this is what I was expecting it to see. This is where we were at, somewhere here. And then it finds the claim. So it is watching for the claim. You can see that it found the claim, db-pvc. PVC is the claim, persistent volume claim. And based on that, it has created the volume with this name and associated it with the claim. That's your provisioning happening here. And this was in a pending state, which is now in a bound state with the actual volume. This is what we were looking at earlier, persistent volume claim. Okay, it was in a pending state, nothing here. Now it has been provisioned, and exactly the same size that I asked for, 2 gigs, is how much it created with the same permissions. And it has been created, it has been associated. Since it has been associated, the pod starts running as well because it found the volume. So this is how the provisioning works automatically. This is the dynamic provisioning in action. Any questions so far?
Yeah, hi Gaurav, this is Dinesh here.
Hi, Dinesh.
Yeah, I'm a bit confused. The reason is, suppose there are multiple nodes. I've
Okay.
got 2 nodes. My DB is running on node number 1. And if I, for some reason, I want to migrate this particular pod to node 2.
Correct.
So until and unless my volume is available on both the nodes, this will not work.
Depends on the type of storage and the type of volume. Will it work or not, right?
Yeah.
Let's take an example of NFS storage, for example. In this case, it won't work because it's a local path. So as you
Yeah.
said, it may not work. So depending on the storage. Now, let's take an example of NFS as a storage class. In case of NFS, the volume, okay, fortunately, this is back now. So let me explain it visually. So if we take example of NFS, what happens is the storage volume is somewhere on the network, right? This is your storage, actual storage.
Yeah.
So the pod was running here. Now it migrated here. It can connect to the same volume and use it, right?
Right.
So in this case, it will work. If it had been local, it wouldn't work. You're right. Right. So it depends on the storage type and storage class and so on. So what happens in this case now? What happens in cases like local storage as a volume? What will happen is the deployment, if you're running it via deployment, the pod will come back on the same node because it knows that this is the node that volume is available on. And even if you create another instance of the pod, like DB, for example, in this case, which should not ideally be the case because every database needs its own volume. Let's suppose there's a web server and you create another instance of that. Even that will come up on scheduling wise, it will be taken care. So it comes up on the same node where the volume is available. That's what you would expect to happen in scenarios like this. In case of network storage, this is not a problem. In case of some other cloud storage like EBS volume, something interesting happens with EBS and equivalent volumes like cloud volumes and cloud storage like EBS, where let's say the volume was here, your pod moved somewhere here. This volume will also move here. It may take some time, but it will move here because this is the network volume. So it will connect to this node. It can connect only one node at a time. So it will switch to this node, and it will basically come up here. Or else all the pods will keep running here, either of that. I think you had a follow-up question to that.
Yeah, perfect. Now my second question. I've got many questions with volumes. Sorry for that. So my second question, yeah, thank you. My second question is that Kubernetes does not take care about the resilience of the volume, I mean data. That means the replica. Basically, Kubernetes doesn't take care of the replication factor, right?
Correct.
It's the storage person or the administrator has to take care of the replication factor.
Correct.
Okay. Now, suppose I have an NFS drive. So when I allot 10 GB, it goes as a claim or it goes as, so 10 GB, I am providing it to the Kubernetes. Now, what happens thereafter? the chunk, what kind of chunk goes to the Kubernetes? I didn't understand. What is persistent volume? Is it the same way that we create a physical volume in while uh, installing the Linux? So what is PV, persistent volume? What is claim? And would you please explain me with that reference?
Hmm.
Thanks.
What would happen? NFS is probably not the best example there, but even if you have an NFS server, what will happen is every time you create a claim, it is going to create a new mount point for you. A new mount point. It's not the same storage or same thing that is mounted on multiple things, multiple places. Every time you ask for a volume, it will create a new mount point and possibly put a limit there. Or let's suppose if it had been a network storage like a cloud storage, in that case, an actual block storage with that much of capacity, let's say you ask for 100 gig of volume, it will create a volume of EBS volume or equivalent to that, and that would be of that capacity, which would be made available to the node. Same with NFS as well. If you have NFS volume created, however it is, it will be available to the node with that much of capacity, and then it can be mounted on a container of your choice.
Okay, that's the reason GFS is so good for Kubernetes.
Right.
So what is Hecate? Because if I go to IBM pages, they also talk about Hecate.
What is it? Can you spell that?
HEI Kitty, something like that. So it's like GFS Hecate. They will. I'll have to check.
UFS Hecate, is it?
Yeah, it's. I'll ping it. I'll ping
Yeah,
it.
if you find it, we'll figure it out, and based on that, we can take that question. Okay, so also when you talked about replication factors and all of that, right? So this is where stateful set is very important. Let me just go ahead and talk about it, right? So let me explain this question first that Dinesh asked earlier. So what about replication factor and sharding and all of those things? Who takes care of it? So we take an example of an application or a database called as Cassandra. Now, Cassandra, what happens is you have a clustered database where you have multiple nodes. It's not going to be one single instance, it'll run on multiple servers. And what happens there is with applications like Cassandra, MongoDB, and a lot of other clustered databases, network databases, and so on, is you need certain things, right? Because who's taking care of, if it had been, let's say, one storage volume and you mount it everywhere, that will essentially not work with these applications. No database will kind of work with this kind of a storage, right? You cannot have a shared volume. You're writing all the data to just one file or one directory, one place. It doesn't work with databases. Database needs its own volume. Every single database needs its own volume. So how will you provision it? Is, let's say there are 3 instances of Cassandra. You need three volumes associated with each instance, basically. That is how it has to happen. Now, when we talk about replication, we're talking about data which is coming into database. Let's say there is a data called as A. Now, this needs to be high available. How Cassandras and MongoDBs make it available is basically by creating their replicas. So who takes care of replicas is the question, and that is handled by Cassandra as the application. So Cassandra forms a ring, and then there using that, it defines the replication factor of, let's say, 2, meaning every piece of information is stored at least twice. Why? So that even if one is down, you have at least another copy of it, and so on, right? I believe, Dinesh, this is what you were talking about.
Yes, absolutely.
Right. So if you want to make this work, you're not only relying on volume and volume claims, but you also will use stateful set, because stateful set will ensure that deployment wise, this is what happens. If you use a deployment, let's say with DB, that's why I said, uh, for DB, this is not the perfect example, because the DB, if you try to do this as a deployment, it will basically create just one volume, and that single volume will be shared across all the nodes of the database, which doesn't work. For DB, you need this. And this is why I said every DB instance needs a volume of its own. So why to use stateful set is just, certain one of this reason is this, because when you create a stateful set, it launches, let's say with a replication of three, replicas being three, it will launch three instances with a volume each. Because with stateful set, you will not have a volume, but you will have a volume claim template. So not just volume claim as in deployment that we've seen, but this is an example of a stateful set for Cassandra itself. And here you see, you don't define the volume. There is no PVC separately defined. It uses a volume claim template, which is a PVC template basically. And why template is because then using this template, it will create as many volumes as your nodes number of replicas are. So if you launch three replicas, it will create three
Gaurav, can
nodes
I
with three
just
volumes.
little?
Yes, Surbi, go ahead.
Yeah, so basically, I would just say, just to clarify it, when we spin up a cluster for Cassandra, when you're talking about the replica, it is not just the replica, it's just the number of nodes we are spinning up the cluster.
Correct.
Replica is defined by each key space definition. Even you have a 10 node cluster, you can have replica of 1, you can have 2, 3, depends on what you want.
That is the replication factor you're talking about, right?
Yes. So yeah.
absolutely.
So when you are saying like, basically Cassandra spinning up, rather than using replicas, the right word kind of should be the number of nodes in a one of the VDC, because it is like, different VDC. It can be like, for example, it can be in US East 1 and US West 2 and like that. So just
Absolutely.
I'm just telling, replica is basically what is number of nodes in a single VDC. Replica
Absolutely.
actually, sorry, just wanted to like.
Yes, absolutely. And this comes from, I mean, just to give everyone a context, Surbi comes with a extensive experience on Cassandra. And when she says the number of nodes, that's absolutely correct. And that is, the number of pods that you run. The only reason why we say replicas here as well is because from the terminology point of view, Kubernetes also uses the replicas in the spec. So when you say replicas, you can read it as kind of number of Cassandra nodes. And why there was this confusion is because Kubernetes has the concept of replicas, which we have to reference or map it to the number of nodes. But at the same time, as Surabhi mentioned, this is not the Cassandra's replication factor. Cassandra's replication factor can be, you can have 10 replicas, as in, let's say 10 nodes of Cassandra running on, different availability zones or same or whatever. You can define the rack awareness and whatnot. But let's suppose even if we have 10 nodes of Cassandra, or let's say I have 6 nodes of Cassandra running here in this cluster, I can still have a replication factor of 2, as in whatever information that is going in, it is stored only twice, not like 6 times. 6 nodes are there, but that is basically, I may have millions of, rows or millions of data points, and those are distributed across different nodes. That's why I want this scalable kind of infrastructure and so on. So my replication factor in terms of Cassandra can be different. There's a replication factor. There is a sharding, partitioning as well. So that can be different. But when we talk about from a Kubernetes point of view, the number of instances or number of pods your Cassandra would run is, we still have to call it as a replica, primarily because Kubernetes references in the spec as the number of replicas here, and that is created by replica sets and whatnot. And that is kind of the differentiation. But everyone should know that this is the difference. We're not talking about application level thing, which is different, and Kubernetes level, infrastructure level. We're talking about how many nodes can you spin, how it spins that, how Kubernetes handles it is what I'm kind of explaining. So thanks a lot, Surbi, for pitching in and kind of.
No, but thank you, Gaurav. You have really explained well.
Thank you. Awesome. So, okay, we have questions or comments here as well. I'm just going to go through it. All right. There's a question from Chana Reddy. I have a scenario where I need to persist the data, multiple folders and subfolders and files inside an image. when I persist the root folder contained inside the root folder and files are getting deleted. I think this seems to be an issue that Chenna has. Okay, he's trying to persist and root folder contents inside the root folder and files, they're getting deleted. You're not supposed to persist the root directory. If you're talking about, let's say I have a pod, if I'm just trying to understand this question, I have a pod and pod has this root file system and so on. And then when we say volume, you take the volume and you typically not mount it as a kind of a root of the pod because that will not persist. It has to be something where you have, let's say, var lib, pg data and whatnot. Now that is where we can use a volume add, right? Not a root persistence here, basically. So maybe that's where all this confusion is coming from, but you can post the follow-up questions there. All right. Okay, Ago has a comment rather than that. So, and he was correct to mention that it should be a stateful set, not a deployment. And we just talked about the difference. So thanks a lot for pitching in. All right, Ashfakar has a comment, more or comment like Cassandra replication factor can be put it in the config map. Yes, absolutely. And that replication factor at the application level, any application level configuration that you have, yes, that can be put inside a config map. And at the time of creating these pods, the config map will inject saying that, oh, your replication factor is 2, and that goes to every single pod. And that can be kept in the Cassandra replication factor can be kept inside config map. Again, just to clarify, I think it leads to the same comment that or confusion, because when we say replicas is 3, this is not the Cassandra's replication factor. If I had to put a Cassandra replication factor, it would have been part of containers, environment, and then something like that, or a config map as you're referring, and that should do the work. So those are the two different things. So this replicas is purely Kubernetes point of view. All right. So Ashfikar has a question about which node the volume can go. How can we define? Now, it's not about volume. It's about which node the pod goes in, right? Because depending on that, the volume will be associated with that node, right? So if your pod is running on node X, the volume will be available to node X. If it is network volume, there's no question. But if it is a volume which needs to be attached to a particular node, it is which node your, let's say your pod is running on, more than which node your volume should be created in. And again, a lot of these questions are related to stateful set. So I'll just explain what stateful set is. Let's say with deployment, we only care about X number of replicas. Let's say web application, stateless application. We say, oh, we want 4 replicas of this application running. We don't care where, right? So it just comes up on any node. Let's say 3 instances of this application to be running. So it comes up on 2 nodes, 2 instances on one node, 1 instance on one node. With deployment, this is absolutely fine. With state, and it can, let's say if I delete it, it will shift to another completely different node, and that is still fine with the deployment. But with stateful set, we want to do it in a certain way and in a certain sequence as well. For example, even the name. If you use a stateful set, the difference between stateful set and deployment, there are a few. So if you look at this, this deployment has launched this pod. This pod comes up with this name. This is the replica set name. And then to make it unique, pod always adds a 5-character hash, which is random, and it's a hash. It's it's randomly chosen to make it unique, to make this pod name differentiate from this one, basically. And since this is unique and random, you can't predict which one is which one. In certain situation, again, let's go back to Cassandra. And as far as I understand, so we can correct me as well. What happens is with Cassandra, the first node, let's call it as 01, right? That node is what you have to connect. All the other nodes have to connect to, because Cassandra has to form something called as a ring, as far as I understand, and the way it worked last, when I used it last. So it forms a ring, and that configuration is picked up from one particular node. Now you need to be able to discover this node, or be able to figure out, oh, this is the first node, right? This is the second node, or this is the third node, if you want to have a need for doing that as well. And stateful set gives you that. Deployment does not. But with deployment, node name is random. It can be anything. With stateful set, it's not the case. Stateful set will always gradually launch the pods. So it's one of the properties of stateful set, and it will have a predictable name. And not only that, it will then bind that pod to that node only. So even if you recreate a pod, like you want to go from version 1 to version 2, it will come back on the same node with the same name. Exactly same node, exactly same name, just a new version, a new pod, same volume. So you can also use a local volume if you want with
Will the
persistent.
IP remain same?
IP will also, IP wouldn't matter so much, because you will always connect with the name, DNS.
No,
And
actually for Cassandra, IP matters actually. That's why I'm asking you.
so
Internally,
you
when they
can't
connect
connect it with the name, you're sure? It has to be an IP
you
address?
know, because what happens is internally when it actually distribute the data, everywhere wherever I have seen it is through IP addresses. So even in in AWS cluster when we used to have it, so we used to have the EIPs, and those EIPs used to be attached to the cluster nodes. So for example, if you have to do patching or anything, right, we will terminate the instances. Obviously the local IP will be different, and when it will come up, it will actually find out the name of the instance, and it will find out the EIP, and it will attach to it.
I understand,
So
but
yeah,
as far as I understand, see, AWS does not give you the DNS always by default, like a name-based service discovery and so on. So that could be the reason why you may want to use a IP, or even elastic IP, which remains constant.
right. And that there is another thing is that, like for example, whatever the volumes is attached to that container, if I'm talking too much, and if you think, it is
No, that's fine.
irrelevant.
This is a good conversation. Go ahead, please.
So basically, the data, basically the data volume which is attached to that pod, or like a node, whatever we say, and that volume has to be attached to that IP address, because that's how internally it is distributed, the data.
So this is all with the premise that at the time of creating the cluster and configuring the
Yes.
nodes, you are basically using the IP addresses. And because of that, everything gets mapped to the IP, which is obvious and understandable. But I will look into this, and we will check whether the IP changes or
No,
not.
it will be a
Anyways,
good learning for me as well, Gaurav.
exactly.
I'm I will be really curious to know what happens with that.
Exactly.
But this
So
is
let's
just my
find out what happens. So I
Yeah.
have Cassandra. The code is slightly older. We'll check if this works or not. We'll also check the code first. This is part of the Kubernetes examples, slightly older code, but we'll find out by launching it. If not, I'll launch another. I'll convert a deployment into, let's say, stateful set, and show you how you can do that as well. So let's say this is Cassandra deployment. It's not a deployment, it's a stateful set. Now, how is it different? One is stateful set has a dependency on service, for the whole reason why that the name discovery is very important here. We don't rely on the IP addresses. Typically in Kubernetes, we rely on the names, DNS. DNS will translate into IP address ultimately, sure. So my assumption is it should work with DNS, but we'll figure out what happens there. So in this case, Cassandra service is going to provide the DNS name-based discovery, because Kubernetes services do that. When you create a pod and have a service associated, you will have a DNS for that pod. In case of Cassandra, it will be very predictable because it will have Cassandra 0, Cassandra 1, Cassandra 2 instead of a random name such as the vote application that we saw here. So these are deployments. So this is randomized. And let's see if there is anything which has been launched with StatefulSet. Nothing. So we'll have to create one. And in case of StatefulSet in the spec, you'll always see the service name because StatefulSet has a dependency on the services in order for it to work. That is one of the properties. You define a replica here. Everything else is pretty much same as deployment, selectors, template, all of that. One other difference here is a persistent or volume claim template. You will not see volume, but you will always see a claim template volume, or no, you will not see a persistent volume claim, but you will see a volume claim template, which basically is a PVC template. So it will create a PVC for every single instance of Cassandra in this case. And in order for this to work, I will have to change the name of the storage class to match whatever I have in the cluster. So that's what I'm going to do here. So there is a stateful set for Cassandra. This code is a bit dated, but it may just work. This has been fixed. So yeah, I'm hoping this does work. Let's find out. So this is a stateful set. We keep everything as is. Don't have to change anything there except for, so you see Cassandra's configuration is here. This is what I was talking about. So in case if you want to use a config map, you can use that as well to provide these configurations, or you can put this as an environment variable like this that we already have. All right. Now, it also has a volume mount. So I'm hoping that Cassandra data is being put on here. So Cassandra data comes from where? This claim template. So every instance will have its own volume. So we'll have to change it to whatever is there. Even if you remove this, if you're not sure, just try removing this. And if there is a default storage class, it will anyways work. Okay, we want to watch what happens. So watch it from here. We want to see the pods coming up. We want to see the volumes claim created for it. We want to see the volume for it. And we want to see the IP addresses also. So minus or wide. So we are talking about pod IPs. Observe that as well, whether it changes, whether it knows. We'll answer that question too. Apply Cassandra stateful set. Here you see it's a replication factor of 3, but it launches one at a time. Okay, always one at a time. You see a claim was created for it using that volume claim template. A claim was created. We have a dynamic provisioning, so volume gets created automatically as well. That 1 gig of volume for this got created. This is okay. This is running state right now, which is good. Let's come up with this IP address of 244.2.36. Remember that there's another 3.36. 2.36 is the one. It is in error state. So this is why I was a bit afraid of, because it's a bit older code. But you get a point, right? What's happening here? Even if this doesn't work, it's fine. And the reason why it probably doesn't work is because the application and the image is quite old or something on that line. I will not debug it right now, but I'll leave it to you to try this out and see if you can figure it out and troubleshoot the issues as well by looking at crash to back office, typically an application issue. So you look at the logs and find out what's going on and all that. Right now, we want to focus on stateful set purely. So I will also show you how to write how it is different. We've talked about it. So it will launch it gradually, unlike pod deployment, which will launch the pods, all the pods at the same time. It will also, have a predictable name, a DNS associated with it always. And let's see how that works. So I'm going to take the existing deployment and try to convert it into a stateful set. Now, what does it need? Let's find out. Kubernetes API reference. I always pick up the one page. And from here, I'll go to the stateful set. So apps v1 kind has to be stateful set. So I'm modifying this. This is boat-sts. Apps v1 is fine. The API version, the first line. Stateful set. And then replicas, we want 3. I'll jump to the spec. So min ready second remains same as deployment. Ordinals, if you want to provide any specific ordinals, you can. It'll start with 0, 1, 2. Number of replicas remains same. So you have the same spec, almost same spec as deployment. There are few changes. One is instead of strategy, you have update strategy. So strategy will become update strategy. And then that may have its own specific configuration, rolling update and whatnot and all that. And it has a partitioning configuration and all that. So I'm not getting into strategy part either. So what I'll do is I'll keep the strategy to default. So I'll remove this part. I'll only focus on the minimal configuration for the stateful set alone. And for stateful set, you define the pod template has to be there. Selector has to be there, right? So the template will be there, selector will be there, replicas will be there. And then one important configuration is service name. So it has to have a service name. Okay, service has to be, it's dependent on services because it needs a discovery at a node, every pod level, not just a application or a microservice level. In case of deployment, you can discover vote, but not, and then point to it, and not like vote-1 and vote-2 and so on. So that's not possible with deployment. With stateful set, that is. Now I will launch it in its own namespace so that we keep it different than existing pods and all that. Create a namespace called as demo, and I'll launch it inside that. I want to start watching everything in that demo namespace now. Same thing I will watch for pods. In this case, just pods and stateful set and service. In the namespace called as demo. It's a different namespace. So we have a partition in which we try this out. And then okay. I'll just change a very few things. One is the namespace gets created in demo. I don't need node port here. Just want some service so that I get a DNS basically. So I create a service of type cluster IP and everything is there. This service is there, and now I will launch stateful set. And the configurer may have to change. Why there is a configurer, if you want to find out, you can check pods. Describe. See the name, vote-0. It's not a random name anymore. Config map is not found. So whenever you see an error, you can describe and you can troubleshoot. And it's a very simple error to fix because I'm have some config map that I say this is must. I will remove this part. I can also set it to not being required and all that, but I'll just remove this part, apply. Keeping it simple. I think it just takes time. I'll delete and recreate. Launch the pod, observe the IP 1.36, observe the name. It'll come up with very predictable names. So you'll always be able to find out that, oh, this is my first node, vote-0, and then it would be vote-1. In about, when it hits about 40 seconds, I believe it will launch a new one, or 20 second gap. So that's probably min ready seconds interval. And then it will launch the next one. 3 replicas. So it has to create 3 and observe which node it comes upon as well. So this is kind worker, this is kind worker 2. And we'll look at that behavior, how stateful sets work and how they're different than deployment, etc. The first difference, of course, is this versus deployment will have names like these. The name of the application, name of the replica set, it launched with, name of some randomized name. So you will never be able to figure out, oh, which one is the first and second and the third. Here it's very easy, convenient to know that. It also binds it to the same node so that even if it gets replaced, a new version comes up, you update it, it will come back with the same name on the same node. It will connect to the same volume. So no problems. The data will be same. Everything will be same. Maybe just the version is different and so on. So it's very predictable, very convenient. You can discover it with this name also, this.svc and something like this, right? So if I go to vote-1, let's try to do that and see what shows up. Ping may not, but NS lookup, depending on whether it is present or not, we will be able to. What should be the pod name? I think I'll have to get the service dot vote dot something like this, instavote or demo. Okay, this part I will try to figure out what exactly should be the name for it to connect from one application to another. This is host vote-1. should be vote 2 or should be one of that, but it definitely is discoverable. Let's also look at the other properties of the stateful set where I will try to delete this and one of this. So let's say we'll take vote 2. It is running on kind-worker 3. It has come up with IP address of 2.37, and this is the one I'm going to delete. And observe the age. Age of this pod is 2 minutes 29 seconds or so. Delete the pod in the namespace called as demo. The name of the pod is vote-3. Zero 3, I think. Vote 3, 2, sorry. So it was running on kind worker 3. IP address changes. So IP is not same. The node name is same. The pod name is same. That is what you see. So Surbi, I'm pretty sure you can do it with DNS. I will just confirm it during our call on Thursday. I'll try to find that then. But I'm very sure that it works with the name, because otherwise it wouldn't even work with the stateful set and kind. It's just
Sure.
maybe it is because on cloud where you don't have DNS space discovery, you're still using IP addresses, but with name it should definitely work. Is my is what I'm thinking, but I'll confirm that.
Sure. It will be a good learning for me too.
Yep. Sure. Perfect. So let me do that one more time. Okay. Vote-2 comes up on the same node, exactly same node, exactly same name. So identity has not changed. It does have a DNS, so that wouldn't have changed either. So I'm just gonna see if it returns this anymore or not. It does. So it just took time for it to be added to the DNS. There is a DNS server running in our cluster. You can see that. So Kubernetes comes with the DNS service. It's coming out of that. And I am on which one? I'm on one of these, and I'm trying to connect to vote-0, vote-1 or something like that, right? So using a DNS, that is, and it does resolve. So NS lookup vote-1, vote-2 may take a few seconds. Vote-0, for example, it cannot resolve. Vote-1 it does, and it is basically, yes, it is similar thing. So this should work for all the pods actually. So maybe my DNS is not exactly working as expected. I'll have to reset my cluster or something, but it does resolve if I use the DNS, the entire fully qualified name of this service basically, which is the pod name, dot service name, dot namespace, and then svc cluster.local, right? That's the convention, and it is discoverable. So no matter what happens to vote-1, for example, right? It's currently 3.38. Sorry. It has been deleted. It will come back up on the same node as earlier. With the same DNS, right? But not necessarily the same, let's say, IP address. So the IP address keeps on changing. And vote-1 is what we were talking about earlier. Yeah, vote-1 has come up with 3.39. They just delay. Or I'm doing the wrong thing. One of that. Okay. Yeah, it does work. I had deleted the pod and I was trying to, you know, I was thinking that I was running the NS lookup from the pod that was deleted. So I had exited basically. So I had to connect back again and rerun the query. And that does work. So 3.39, it has picked it up for itself, but it can be another pod as well. And it should return the similar thing because we have a DNS, resolving all the services, and each and every pod in our, let's say, each and every pod is being resolved with a DNS, and that's how stateful sets work. And if you have a, let's say, as I showed you here, storage wise, we have a dynamic provisioning where every pod which requires a claim or a volume, you can associate it with a claim. Sometimes you have one volume which is shared across multiple instances like web servers, stateless applications, and so on. Or sometimes we have stateful application where we need one volume per instance. And that's what it is trying to do here. It doesn't proceed from here because there is a pod crashing. And you can figure out what the issue is by typically looking at maybe start with the logs. In this case, that's what I would begin with for this pod called as Cassandra. And then it will basically you'll have to figure out from there on, right? What happens next and all that. So it's has an issue here while coming up. And this is probably where we'll have to figure out what's happening with Cassandra and leave that to you for trying out if you want to, right? I've shared the repository. The code is slightly older, maybe updating the image here may do the trick, right? Because this image may have been updated maybe a year ago or two. So as far as I see, the last commit here was quite a while ago, right? And that's probably the reason why you do not see this working or something on that line. But as far as stateful sets and volumes are concerned, this is how it works. So you have, I'll explain visually how the provisioning, dynamic provisioning works one more time. So we have, let's say the pods. Pods have volume and volume mount. And instead of, configuring the type of volume here itself, we reference to a claim basically. Now, earlier, what used to happen was this was a manual process before 1.16 version of Kubernetes, where somebody would have to create a volume for you, typically an admin, and then only it gets associated with the claim. It remains with the claim so that even if your pod comes back up, gets replaced, the volume is associated with the claim. Claim does not get deleted automatically when the pod is upgraded or replaced and so on. So the PVC remains, the volume remains, and you can still consume it once you have the pod back up. Now, this was a manual process that was then automated with the storage class. And storage class is a configuration that the admins provide typically. And what if we provide there is like, this is the kind of storage which is available in the cluster and how to provision it. Either it is an internal provisioner or it can be a provisioner that you launch inside the cluster like we have for the local path. And that provisioner then will interface with backend storage if needed, create the volume and make it available to the claim basically. That's how the dynamic provisioning works. A lot of this depended on the storage classes being available with all the code to interface with the backend storage, from Kubernetes itself, right? So that kind of, made Kubernetes code heavier. Plus, if you were a storage provider, you had to depend on the Kubernetes's revisions, like new version of Kubernetes gets released once in a quarter, for example, right? So you had to depend on that for any changes that you were making. And that was a lot of dependency, plus everything had to be reviewed by the Kubernetes team because it was part of the Kubernetes code base itself. And that is where the new thing that has been introduced now is CSI. And that is the reason why you see a smaller table right now. There was a huge list of storage classes which were supported earlier. That is shrinking because with every version of Kubernetes, they are moving it to the CSI. CSI stands for Container Storage Interface. Gives you a lot of flexibility. So Kubernetes already has these interfaces. A couple of interfaces we've already seen include CRI. So that makes Kubernetes independent of the runtime. So when Docker was replaced by something else like Containerd or Cryo, nothing changed really because it was just an interface, and Kubernetes kept on running the way it always did. And if you wanted to make your container runtime compatible with Kubernetes, all you have to do is comply with CRI calls. It's a language. So Kubernetes says hi, you should know what to say, and you will say hello or something like that, right? So if it is a completely alien language, you wouldn't know how to answer. So if you know the language, you need to know the language and need to be able to respond. If that works, you are compatible with Kubernetes. That's the CRI, a runtime interface. They have a CNI, which is a container network interface. So you can bring in any plugin, any way you want to network. It's possible. You just bring in a plugin which is compatible with CNI and it works with Kubernetes. Same thing with CSI, where the code will not be hosted with Kubernetes' code base. It will be independent. Kubernetes will define the language. Oh, this is how we call for the volume. This is how you respond. And if you know the language, if you are compatible, you will work with Kubernetes. And then you can manage your own release cycle. You are independent of Kubernetes. Anyone can create their own storage provider. And that is what we are moving towards. That is what CSI stands for. So the future is CSI. Right now, when we are in a process of transitioning, so you will see storage classes, you'll see volumes there created with storage classes and provisioners versus you can also use a CSI interface and then kind of just let it be managed through that as well. So that's where we are moving towards in the form of a volume and how the storage is being managed, etc. Any questions here?
Quick question.
Yeah.
How
Yes.
useful are these? Do you really recommend for databases to use, Kubernetes parts? Typically, like, we always use like outside of Kubernetes, the databases, right? That is what recommended approach.
So far, yes. So most of the databases remain outside of Kubernetes for various reasons. Few being initial versions of Kubernetes did not have this stateful set. They used to call it as, they started with pet sets. There's also a very interesting story behind why it was called as a pet set was because Kubernetes, when it was created with this concept of pets versus cattle. So what is this pet versus cattle, right? I can relate to this very closely because I have lived in the world where we had handful of servers, like a few hundreds of servers maybe. And we used to name them. We used to treat them as pets. And I've seen this personally because we had certain names for certain servers, and I exactly knew what is hosted on which server, what data exists, and what configuration exists in my mind, of course. But that's not the right way of doing it because then you create this staff-like infrastructure, which is difficult to replicate. So if you had to replicate, you have to figure out everything, and it's almost impossible to replicate the same way. And you're too much dependent on a particular server. If it goes down, you're kind of dependent on it, right? And beyond that, when you name it and you treat it like, it's like your pet, right? You get attached to it and so on. That was the concept of pets and treating servers as pets rather. And then Kubernetes changed it because with Kubernetes, we're talking about immutable deployment. It's all replicable. Everything is automatable. And you're not worried about what is running, which node. You don't even care about which nodes, and you forget about naming those nodes as well, right? So you're treating them as cattle, basically, your servers and your farm of cattle So farm of servers and just pool of servers to serve as a compute capacity. And that is how it started with, the whole concept of pet versus cattle. But still, Kubernetes came from Google, right? So they don't have this concept of storing the state on the server itself, right? They always created this microservices decoupled architecture where the data is stored somewhere, managed some other way, and you don't run stateful applications at all, kind of, right? And that is why Kubernetes did not support this at all, right? And they created pet sets initially, which became stateful set later, because it's more about stateful applications. So that is how it happened. And since the story, it evolved much later than after Kubernetes. One is there's always kind of less confidence in using it. Second reason also is if you use databases, sometimes I would say managed services are better also, in a way that all the replication because if you use, for example, on AWS, if you use a managed database, on Azure, if you use a managed database, those databases have been configured with a lot of factors in mind, like the disk level RAID arrays, for example. It's been configured with that. It takes care of automated failover, takes care of database replication, which itself is pain to manage in case of relational databases, which I've done with Postgres, and we had to reset the databases, we had to monitor the replication. So there's a lot of work and overhead in managing the database, and that is handled very, very well by these managed databases. Sorry. And that is the reason why still databases are primarily hosted on outside of Kubernetes. But it is possible, if you want to do that with StatefulSet. And there are other use cases beyond databases as well, which you can host on Kubernetes. You have any other stateful application, you don't have a managed service to do that, you will use StatefulSet to do that anyways. Some databases, like scalable databases like Cassandra, it's still okay. You can still consider to host it on Mongo and Cassandra on Kubernetes, because inherently it offers application level replication, sharding, scaling, and stuff like that. So those you can still host on Kubernetes. But if you have relational databases like Postgres, MySQL, and Oracle, maybe, I would still say you may want to still stick to the managed database services. Those are very, very good in terms of overhead of administration, managing, and so on. But there are certain applications, including Cassandra, Mongo, you may want to try out, consider, let's say, using Kubernetes for, and others are just better on managed ones. So that's what you see as a typical trend, where most of the databases still exist outside of Kubernetes.
Yeah, got it. Thanks.
Yeah. All right. Okay, so again, there's some comments that I see from YouTube Live. One of that is Chen already mentions about the same IP address versus DNS, and he does mention that DNS does work when you switch to it instead of IP address, and that's what my assumption was. Even for Cassandra, it should work. And about your volume, I think we'll have to kind of figure this out. So Chena, if you're part of our community of members, or if you're a member, do join in our Thursday session. We'll take it up. If you're not, you can join the Geek membership, which gives you access to the Kubernetes bootcamp, all the projects, and also the weekly live sessions that we do on Thursdays, where you can bring in questions. We can dive deeper into it and look at these issues, and maybe take more questions from there as well. All right, so Cedric, can you describe your issue? You seem to have an issue with Kubernetes cluster node setup. Can you describe it? What are you using, whether you're using kind, whether you're using kubeadm, and your worker node saying not ready? That could be because of networking. If all your worker nodes are not ready, I would say check if you have set up networking or not, CNI. Launch the network. and see if that works for you. You'll have to figure out the networking part. Most likely it happens when the CNI plugins are not up and ready. So you may want to use one of the plugin configurations, make sure it is up and available. That's how you'll have to debug. If not, you try to see if you can have the setup available with you. And on Thursday, we will just connect to it and look at it. You can reset and try it out as well again. And if your one node is ready, the other one is not, then it's a bit challenging. Then you probably have networking configured, but it's either not running, crashing on one node. Maybe there's a problem with the host name, DNS, and so on. Make sure your host names are unique. That's also very important. Otherwise, you get into a lot of issues like this. So check host names, try to reset networking, try to reset cluster once. If not, bring it up, have it ready on Thursday. We will kind of look at it as well. Yeah, so since it worked on after resetting for node 2, try doing that for node 1 as well is my suggestion for you. If not, we'll look it up on Thursday. I think we will close the session there. Most of the questions have been answered. Vivek has a question: using Ceph, can we get free of overhead replication factor? Yes, maybe, but we still have replication at the level of Cassandra and database application and all that as well, right? So that's a different thing. So when we talk about replication of storage, that's a different, at the storage level, you may have a replication at like a RAID array and all that stuff as well. But there are multiple aspects here, right? Dimensions. So one is at the storage level, another is at the application level. When we talk about replication, and the one I was talking about, the overhead, which is handled by managed database services, it is the database level replica is what we were talking about. And that's, you will still have to deal with no matter what kind of storage that you use, Ceph or otherwise, right? So that's the database level replication, right? So that's difference between disk level, maybe at the storage level is at a similar level, and then you have application where you have to deal with that as well. All right, so with that, we will conclude our session for the day. We'll come back on Thursday. For the members, we have a call on Thursday. Otherwise, we're going to come back next Tuesday and we'll start talking about security, namely RBAC, a little bit of network policies and the security context, right? I hope by the time we come back next time, I'm completely recovered with my voice. I'm getting better every day, but it's still a little bit of an issue when I do a longer session. So next week, I hope to be completely fit and fine. And we'll conclude our session here. I'll see you next week. Thank you. And bye-bye. All the best.